Great. Well, thanks for having me. I want to tell you guys a little bit today about some of the things I've been thinking about with field theories in this Stolz-Teichner program. So very roughly, Stolz and Teichner have been working on certain definitions of smooth geometric field theories that seem to have some natural home in topology. And it's a bit of a mystery, to me at least, where exactly that natural home is. And I want to give you some ideas today about kind of the flavor of this approach to studying manifolds. So the beginning of the story goes back to Siegel, who proposed that one think about manifolds or the topology of manifolds by studying families of field theories over them. So I'll make that more precise in a bit, but just bear with me. So study manifolds by analyzing families of field theories over them. Okay, so I guess this originally was supposed to understand things related to elliptic cohomology, but you can generalize this approach. And Stolz and Teichner have done that. They have this construction. That for a fixed superdimension, d delta, we get sheaves. I'll denote d delta EFT for Euclidean field theory. Actually, you get a sequence of sheaves, twisted field theories, that are on the side of manifolds and land in, say, pointed groupoids. Okay, so these are very geometric objects. I want to emphasize that these are groupoids, pointed groupoids. If you like, you can replace that with simplicial sets or something like that. I mean, this is kind of a general story, and depending on the definitions, you can kind of massage this data. But the point is that these things have a very geometric flavor. They're like families of vector bundles or elliptic operators or things of that sort on manifolds. So far, there's no topology. This is just some kind of generalization of geometry.
These are sheaves on the category of manifolds?
That's right.
On Nietzschean manifold?
On the category, yeah. Yeah, so these are contravariant functors. There's Z many of them. You should be thinking like maybe there's a spectrum lurking somewhere.
And is that category of manifolds all smooth maps?
All smooth maps, yeah, all smooth maps.
You say EFT.
Yes, E is for Euclidean. So you're allowed to change this, and I'll try and explain in a little bit what I mean by Euclidean. But
category of manifolds is sensitive to Riemannian structure.
So far as it's stated, all I'm looking at is the manifold as a smooth manifold, no extra structure.
But you're still calling it Euclidean.
Okay, so maybe I better say something, because I think I know what you're saying, and this is a little different. So these are
Fit with the second sentence?
the first sentence. This first sentence and this? Yes. So let me explain why. So, okay, so what do these d delta field theories look like evaluated on a particular manifold, X? So these are functors, symmetric monoidal functors, from a certain Borzum category over X. So what that means is that I have these d delta Borzums, that's some supermanifold, equipped with a map to X. And this Euclidean means that the supermanifold has the Euclidean structure, but X is just a smooth manifold. Does that answer your question, Hiro? OK. So I guess while I'm here, I should explain what this K means. So this is a definition of untwisted field theory. So you put a 0 there to get this thing. And then for K, so a twist, say tau, is a functor. So we start from the d delta Euclidean Borzum category over X. take tau, and you go to, say, algebras, bimodules, and intertwiners, then you can consider the constant map that goes to like the unit over there, C as a CC bimodule, or R if you like. And then a twisted field theory.
What is
Algebras, bimodules, and intertwiners. That's a bicategory, symmetric bundle bicategory. So a twisted field theory, or maybe a tau twisted field theory, is a natural transformation. E. So this E is in, say, D delta Euclidean field theories twisted by tau over X. OK, so this is a lot of, yeah?
I didn't understand the definition of a twist.
Yeah, let me give you a better way of thinking about it. So here's the formal definition, and let me say, sorry, the twist is just this thing, if that's what you mean.
And E.
So sorry, this is combining two things at once, which maybe was a bad idea. So the twist is just tau.
Okay, this tau is just the functor from that to alpha.
That's right. So think about it as picking out your favorite algebra. Let's say it's a Clifford algebra, because that's one of my favorites. So then a twisted field theory is going to be one of these natural transformations that's going to endow these field theories with some kind of Clifford action in this case. So you should think about a twist as picking out your favorite algebra, and twisted field theories are like taking vectors in modules over that algebra, very roughly speaking, rather than vector spaces. So vect is a nice module over R or C, and this is changing that to something else, this tau. Sorry, I don't think I wrote this very well, but is it clear?
Tau is 1.
Yeah, so then it's just vector spaces.
No matter how I pick E?
That's right. Well, I mean, sorry, if you pick tau to be 1, the natural transformations between 1 and 1 are the same as these sorts of functors. So untwisted is the normal definition, or the trivial twist. OK. Right, so far we're just doing geometry. So far there's no topology anywhere. So let me tell you a little bit about how to get topology out of this. OK, so to extract topology, we consider the following. So I'm going to take X and map it to what I'll denote by this d delta Euclidean field theories with square brackets. These are concordance classes, but let me give a slightly different definition. So these are going to be pi 0 of a certain simplicial set. So I can take the nerve of this groupoid evaluated at a manifold, and then I can add in some smooth simplices when I evaluate this thing. And then that's a bisimplicial set. If you like, I can geometrically realize it and then take pi 0 of it. And these are these concordance classes. And then the claim is that this is an additive homotopy functor. N dot is taking the nerve. So this is a groupoid. You can take its nerve. It's very close. If I didn't have this, I'd be taking isomorphism classes.
Sorry.
But yeah. So if I ignore this, this is just isomorphism classes. When I throw this in, it's a little bit weaker. It's kind of looking at paths in some space for which this is the functor of points, and it's like connecting, well, taking pi 0. So connecting things that are related by a path.
So maybe you already said this, but what's the choice of tau you're making here when you're indexed by K?
I'm suppressing that. So yeah, I guess, let's see. This is what I have in the back of my head. So I have a fixed tau. I take some tensor power of it. And then a tau tensor K. Twisted field theory is one of these guys, like this.
What do you mean by ante?
So disjoint unions go to sums. Disjoint unions of manifolds. This is just from the sheaf property, actually, that these guys form a sheaf. So if I take a disjoint union, I can evaluate sections in an easy way.
So is that the definition of like the k up there? Means you take your twist and tensor the entire?
Yeah, so this isn't perhaps not the best notation because tau is somehow in the back of my head and I have it fixed.
Confused about go to sums. I mean, what is sum?
Can we discuss that? I mean, there's some different versions of this depending on. Is it okay to leave that for later, or? You should be thinking about this as a sheaf again. So if I take disjoint unions, whatever is going on over here, I'm taking like the sums of sections. Then when I take concordance classes, it's still a sum product, I guess. You seem unhappy.
So you're saying things like, well, say you have two vector bundles, you can add them.
That's right.
And these are objects of that type, you can add these things.
Yeah.
So what is consciousness?
Okay.
And
So.
it's like a nerve of a bias.
Well, the nerve gives a second simplicial direction, and then I can take the diagonal.
Then sorry, the nerve or the delta give the second simplicial?
Well, it depends on which one you do first, I guess. So yeah, I do this one first, and I have a simplicial groupoid. And I take this and I have a bisimplicial set. And I can take the realization if you like, or just do something more combinatorial.
Can you say something like you first realize with respect to delta simplicial thing in the category of groupoids, and then take isomorphism classes?
Yeah, these things don't matter. I mean, I can realize along the diagonal or whatever order I want.
I mean, somehow my problem was somehow there's this abstract disjoint union. You have
Yes.
disjoint union, and then you connect with a sum which is somehow intrinsically defined in the field theory. So there must be some point where you couple these two operations. And we have the sheaf. I mean, somehow you get the disjoint union of copoids from the sheaf axiom, but now you couple to the internal sum.
I mean, I'm a little confused. If I have a disconnected space, say 2 components, I can cover it with just each component separately, and then I can write down the limit for the sheaf, and then I get a product. Is that? I'm really just using the sheaf property here. That's all I'm saying. And then an equivalence relation. Okay.
I'm a little confused. So is square bracket x different from what the functor assigns to the manifold x?
Yes. So is that? I mean, this is defined as this, which is not the same as this.
I understand.
So let me maybe just say a little bit more about kind of what the logic here is. We start with this very geometric guy. It's doing something like looking at vector bundles. We have this twist in the game as well that looks at sort of bundles of modules, say. And then we're looking at those up to some equivalence relation which guarantees that we satisfy homotopy invariance.
More lowbrow approach to this equivalence relation is to say, well, you take concordance classes of these field theories, just meaning two things are concordant if you find a field theory where x crosses a unit interval which restricts to the two given things. But that's a different way to say the same thing.
Yeah, I guess the point is that to compute pi 0, I only need to know the 0 and 1 simplices. So that's what Stephan's saying. OK, so now we can ask all kinds of questions about this, but maybe I should give a quick example to show that this isn't the most crazy thing. So yeah.
So in the context of just TFTs, you know, the symmetric numerical functors that are the logarithm category to some infinity n category turns out to be a groupoid.
Yes.
And natural transformations are always invertible. I mean, is there something similar you can say about the Euclidean logarithm category, or is that just not? This is just me not understanding the
Are you asking if all of, that all natural transformations between functors are invertible? That's the question, or? That's generally not true, but since I'm taking this nerve, I'm only seeing the invertible guys, or I'm formally inverting, or whatever you like. So we might as well just consider the invertible guys, I think, is the plan. There might be reasons that I don't understand yet as to why you might want the non-invertible ones too, but for now, yes, look at the invertibles. OK, so an example. Okay, so if I look at 0, 1 Euclidean field theories of degree k, or actually just of degree, say, bullet, this is a sheaf on manifolds. It turns out that this is a discrete groupoid, so it's just a sheaf of sets. In which sheaf of sets is it? Well, it reads off closed differential forms. So this is the type of thing to keep in mind, that we have some sheaves that are very geometric guys, and then when I do this concordance relation, well, this gives me Theorem cohomology. So this is a nice homotopy functor.
Can you say what tau is for this example? If you don't want to, that's fine.
So tau is not an algebra because we're in the zero categorical setting. Tau will turn out to be a certain line bundle over a certain groupoid that I can tell you, but it's it would take me a little bit away. Yeah, in these zero-dimensional cases, things are not quite this complex. There's some, rather than vect, you just have the groupoid R with multiplication, or C. And then this is just like pick or something rather than algebras. Okay, so maybe we're lucky enough that this always happens, right? This isn't just a homotopy functor, this is a cohomology theory. These are great because we can compute them, and there's a wonderful theory. So one might get really excited about this and ask, well, we have additivity in the homotopy axiom, so do we always get Meyer via torus? And this is a little ill-posed, as I'll describe in a minute. I mean, the Meyer via torus sequence is actually extra data. You need a connecting homomorphism. So right now, this is an ill-posed question. But really, the right question is, can we equip the sequence of functors with the data of a connecting homomorphism such that we get Meyer via torus sequences? But even then, the answer is not always. It's very interesting to figure out when you can. That's the content of the mainline Stolz-Teichner program. But there are these cases where it just doesn't happen. So then when someone hands you a homotopy functor that doesn't have any really nice properties, how do you actually extract invariance? That's really hard in general. But I'm going to describe.
I mean, one question. You say
yes.
Always. I mean, the only parameter I see is d and delta. So
and this twist, yeah. So for any d and delta, do we get? So fix your favorite d and delta, fix your favorite twist, and you can ask this question.
This is a parameter. They say sometimes.
Yes. Yeah. So I'll be more specific when I say not always. There'll be some examples where it doesn't work.
But you always get a sheaf.
You always get a sheaf. Yeah, but yeah. So Meyer via torus is closely related to like a homotopy sheaf property, but these are sheaves that kind of don't talk to one another so far, right? For each k, I have a sheaf, but there's no relation between them.
And what you've done is you've taken this sheaf bound in groupoids and done some funny construction to it because you get possibly sheaf value sets.
This is not, in general, going to be a sheaf. I mean, closed forms are a sheaf, but Theorem cohomology is not. So this almost always fails to be a sheaf, this concordance classes. But that's kind of a good thing, because if it were, then you wouldn't be seeing interesting global data.
Sorry, in the example, you really have bullet going to bullet. You don't have sort of bullet going to product of parity of bullet.
So this should be even and odd, and this should be even and odd. Ryan knows the theorem, so yeah. If I put a t here, which wouldn't conform with everything else, then I could just write it like this. But I want to talk about Euclidean today. So
in other words, you get into periodic version of the
yes, exactly. So with these Euclidean field theories, actually in any zero-dimensional Euclidean field theory, you end up with some two-periodic guy over here. In this case, the two-periodic version is two-periodic Theorem. So I see all the even forms, all the odd forms. And when I take concordance classes, I see all of even cohomology and all of odd cohomology. As we'll see, this is closely related to the fact that this is the right target for the Chern character. OK, so yikes. OK, so the next question is, what structures can we use to extract computable homotopical data from field theories. Okay, so I need to describe some structures about field theories that would make this make sense. I mean, it's going to be roughly along the lines of where's this connecting homomorphism in Meyer-Vietoris, kind of intrinsic to the land of field theories. So with closed forms, you know that the suspension homomorphism is really related to integration of forms going in one direction, and there's a suspension class in the other. You can interpret this integration map in field theories as some kind of quantization, and that's the structure that I'm going to exploit in large part. Another structure is related to kind of this Chern character observation. It's called dimensional reduction. So playing dimensional reduction and quantization off each other, we can try and make some progress on this question, and that's what I'll spend the rest of the talk describing. Okay, so I think we're ready for some giant diagrams. Actually, yeah. Okay, so I'm going to start with looking at D/1 field theories, give you a bunch of examples, and tell you how these things relate. So I'm going to start over here on this far side. It's a shame that, so 0-1 field theories, remember, were Theorem. So I have this map that I mentioned called integration of forms. I can do this in families. If I have a fiber bundle x cross y over y, or more generally any kind of fiber bundle with fiber x, such that I have an orientation, which I'll write like this, on these fibers, I can do this integral. Okay, so Arturo discussed yesterday the relation between 1-1 field theories and index theory, Dirac operators. And similarly, if I have one of these bundles where the fibers are equipped with spin structures, I can write down this map. So this is close to, well, Arturo can tell you exactly where this project is, but we expect a map like this coming from index theory. Now, for 2-1 field theories, this gets a lot harder. Somehow, dimension 2 is sort of the borderline where analysis gets really crazy with field theories. But still, if you believe the physicists are honest people, then there ought to be a map like this, some kind of quantization map. OK, so these are the types of things I'm going to use. Now, this is a string structure on the fibers of this bundle. Don't have a whole lot of time to go into that, but roughly it's like a spin structure on loop space. So we're seeing something about loop space geometry on this far left part. OK, but there are other things here that I haven't drawn arrows to yet. So what are these? Well, over here, I have this map that's called dimensional reduction. Naively, this is just crossing with the circle. If I have a 0-1 dimensional manifold, I cross with the circle and get a 1-1 manifold. In all honesty, it's a lot harder than that because that doesn't translate into the Euclidean world. If I have certain geometric structures, I can't always split them into products. Like, I can't split a symplectic manifold into a product of 2 odd dimensional manifolds or something like that are symplectic. That just doesn't make sense. And then similarly here, I can't split this 1-1 Euclidean manifold into a 0-1 and a 1-1 Euclidean, or a 1-dimensional Euclidean manifold. But in any case, this has been constructed by Fei Han and Peter and Stefan. It's this nice map. In fact, he shows that it factors through this kind of loop space stuff that Scott described yesterday. So there's some sort of field theory over the loop space, and this Chern character map factors through that thing. Or sorry, dimensional reduction map factors through that thing. OK, well, we can do a similar thing up above. We can get all of these maps as well. By the way, red stands for reduction. So unfortunately, there's no color that begins with Q that we have up here, but green is for quantization.
In the factorization,
Yes?
either of the map is not variable.
Oh, sorry. There should be loops of y right here. Is that right?
Is either of one easier than the other in the factorization?
So the question is this arrow easier than this arrow?
No.
Or
in the factorization, you have this way.
Oh, this arrow is sort of trivial. You just pull back along the constant loops. So I can think of Y as a subset of the loop space as the constant loops. And this is the easy one. This one and this one require work, but they're sort of different kinds of work. This is one that I've been writing down recently, and then the other one is due to Fei Han. OK, so this is kind of the picture of the structures that we get. And then there's this wonderful mirror in the topological world, or the stable homotopy world, that I want to describe. All right, so this is kind of, OK. So up above, we see de Rham cohomology, K-theory, and TMF. There are all of these push forwards that go between them and various maps that are kind of analogous to the Turing character. This one below is evaluation of TMF at the elliptic curve. So this is the universal elliptic cohomology theory. In particular, I can ask for it at a given elliptic curve, and then I get this power series in K. If I set t equal to 0, I get back here. And the precise relation between these two things is not yet fully understood, but you can almost, well, you can imagine seeing z-graded vector bundles over Y by restricting to the constant loops and remembering this circle action. And that's kind of the relation between this thing and this thing. So a circle action on a vector bundle will give you a z-grading. OK, so this is great. We have this wonderful world of field theories. There's all this nice connection to geometry. And we hope all of these sort of maps. Yeah?
To explain this map from K-theory to the cohomology of the
Sorry, from this to here? Well, that's what we heard about yesterday. I mean, sorry? OK, well, I'm not saying that this is de Rham on the nose. I'm saying that there's some, I didn't put de Rham subscript here. There's some group that lives here. Is that good enough for now, or?
Well, it's not the, I mean, it's again not the ordinary equivalent cohomology.
Yes, I agree.
It's something else.
Yeah, I put this symbol here, I guess, slightly dishonestly to denote the right group that sits here, which is, I agree, not equivariant de Rham of loop space. It's something else. But it factors like this. OK. All right, so we want to do this for higher dimensions or other field theories. So I'm next going to look at the case where I just increase this supersymmetry by 1. So this is getting fun. I get to do this again. All right. OK, so I have.
Sorry, before we go on to the next diagram.
Yeah.
I guess didn't like Pope and Chung sort of construct.
Yeah, sorry, I should have mentioned that.
Theory sort of inconsistencies?
Yes. So in a slightly different language, Pokman Chung showed that there exists a map from here to here, but it's not quite here. It's a slightly different category. So actually, I would say that probably in, so I haven't quite checked this, but I believe it to be true that he constructed a map from here to here, which is roughly this one I'm saying, that you restrict this S1 action to the constant loops, you see a z-graded vector bundle, and bang, you get a map. But I'd be happy to discuss that more later, but that's what I think the picture is from Pokman Chung's thesis. OK, so the next diagram, we have more supersymmetry.
And an EFT, what, like that 2-1 over there, what kind of surfaces are involved?
Right. So so Euclidean means flat Riemannian geometry, but in the super sense. So we're seeing super cylinders and super tori inside of X, and that's it.
So just cylinders and tori with flat structures or something?
Yeah. So the super thing is really, that's kind of the important, it's the meat of the matter here. And what that does is it takes an odd square root of one of the even directions. So you can imagine down one case lower that the Dirac operator is like a square root of the Laplacian. It's a similar story up here, that there's like some square root of some operator coming from the supersymmetry, if you like.
What's the bosonic part, the 2 part?
Yeah, the bosonic part is just cylinders and tori. Yeah, flat with flat structures. Yeah. Somehow all of the complications here come from the supergeometry stuff. The sort of the underlying bosonic Borism category isn't that fancy. Well, that's kind of a lie, but it's not. The supersymmetry is what makes this work. OK, so over here we have some other family of field theories. There's a nice map here that's basically analogous to the one over there. It's some kind of integration map. The difference is that rather than things just converging all the time, you have to worry a little bit because it turns out that while these are finite dimensional objects, they're non-compact. So this is an integral to a Gaussian measure, actually. So it's like an integral with respect to some kind of e to the minus s. I'm writing s for action, and that's exactly how you build this thing, is opening favorite physics paper, seeing what they put for this action, for this amount of supersymmetry, writing it down and checking that it works. Now, there's a similar map here that's kind of in the same state of limbo as Arturo's map, but for different reasons. The one here, you can think about certain objects up here as being flat vector bundles over X. Those give examples. And this map would take the twisted de Rham complex with coefficients in that flat vector bundle. So rephrasing of that is to consider the Morse complex twisted by this flat vector bundle. And then this map boils down to combinatorial data. I can look at critical points of a Morse function, look at the fiber of my vector bundle over those points, write down some differential related to gradient flow lines, and get this without doing very much analysis. But then you have to prove that it satisfies all the properties, and that's where this is hard. So there's a candidate for this map, but you have to prove that it does what you want it to. Up here, the situation is a little bit more perilous, much like the other example. If you want to draw this analogy as before, that 2-1 field theories are kind of trying to do sort of analysis of Dirac operators on loop space, these 2-2 field theories are trying to understand the Morse complex of loop space. So understanding this amounts to seeing the sense in which you're actually doing Morse theory of a loop space. Yeah.
Can you go back one step and explain
Sure.
why this Morse theory?
Sorry, what?
Can you go back one step and explain why that error has to do with Morse theory?
No, but let me tell you where I found that out, and I can discuss it with you afterwards. So maybe I'll say a little bit more. Maybe no is too quick of an answer. But this is from Witten's paper on supersymmetry and Morse theory. All these geometric structures come from that. You have two odd square roots in this case of a Laplacian. What are those? Well, they're like d plus d star and d minus d star. So you can form linear combinations and get chain complexes, all this kind of stuff. And if you do it carefully, you also see the Hodge star in the game here. So that's not quite what you were looking for, but that's the starting point, is to notice that, well, the de Rham complex furnishes an example of one of these field theories. And it's like the quantization in quantum mechanics of some guy, and that's why this map is related to the de Rham complex. And then you do Witten's trick, and you see that the Morse complex can also be a candidate for this quantization map. OK, so great. We have this. We also have all of these dimensional reduction maps as before, kind of for similar reasons. I guess this one I haven't yet finished constructing, but totally believe it exists. This is the easy arrow. This thing exists. This guy works. You have all of this same kind of structure. Oh, maybe I should mention, I don't know what to put here because I don't know what flavor of Morse theory we're doing, but this might be related to Dennis's question earlier in the week that perhaps this is some symplectic orientation or something like that for this wrong way map.
You have the map facing through slanting down that.
Yeah, this guy, yeah.
But you don't have the map sort of slanting down that.
Yeah, I mean, this reduction is somehow very different than this one. This one you're trying to reduce along something that has odd square roots, and this one you aren't. That's maybe the one way to say it. So yeah, I mean, I was more excited to do this one, and this one looks like it's going to be a bit of a pain, but it should be there.
Could you say again where the non-compactness? I mean, wasn't?
Yeah.
I mean,
Yeah.
Like, what is non-compactness?
Yeah.
Wasn't
OK, so I suppose you know a little bit of supergeometry. Let me just say roughly what's going on. These Bordisms are maps from R01 into some manifold X. That's the odd tangent bundle, functions on which are differential forms. Over here, the Bordism category is maps from R02 into a manifold X. Well, there's this even square zero function on R02 that's the product of the two odd guys. And that gives you some even derivation, which tells you that the underlying space of that mapping space is actually the tangent bundle of X. And that's the non-compact direction. As you increase the amount of supersymmetry, you still see all these non-compact directions. So these Gaussian measures become absolutely essential once the super direction is bigger than 1. You can't hope to write down this map without it. OK, so what goes above? I don't know. I guess it's a fact that these aren't cohomology theories. That's maybe one way to say it. So an anti-theorem, I suppose I would like to call this. D2 EFTs don't have Meyer-Vietoris sequences. So this was a big surprise. I always thought that the sheaf property would kind of guarantee it, and it just doesn't. So what fails here is a suspension isomorphism. And
What do you use as abstraction against? Like, I mean,
how do I prove this?
yeah, so what is the abstraction against? I mean, if you have just a sequence of sheaves, what is the abstraction against?
No suspension, no existence of suspension isomorphisms.
Yeah, I mean, yeah, but how can you see it? I mean, because
I'll show you later. Yeah.
You know in which word you have to search for.
I totally agree. Yeah. Well, OK, so there's one stupid answer, which is you compute, and you know what cohomology theory you'd have to get for 0, 2. So you can just look at the coefficient ring of the proposed cohomology theory here, and you see R. So you have to get some wedge of KRNs, and then you compute the value on the torus, and you get the wrong answer. So you cannot find Meyer-Vietoris sequences. And then from that, you can bootstrap up. I mean, I have this data of these quantization maps, at least the candidate in mind, and that's what's allowing you to make this statement. And I'll explain how that quantization is related to the suspension isomorphism right now, I think, actually. So, OK. Oh, so just a few remarks before I go forward. So you might think that, well, if this is the only example, maybe this is going to be solved soon. But this is just the tip of the iceberg. There are many, many more supersymmetric Euclidean field theories that should have the same sort of structure. And I have no idea what they're doing. So a similar picture should exist for D4, D6, D8, and D16. And by the way, these things continue beyond 2. I just don't know very much about, like, these are already hard enough, and so I didn't keep going. But this one stops at 3, and this one actually stops at 2. In general, the relation between how high you can go in D and the number of supersymmetries is some sort of spin representation type numerology. So these are all finite families, but there are lots of them. OK.
See, I kind of missed some of the fragments.
Sure.
So you always get a homotopy functor, and the question is whether or not you have the algebra, the full sequence. Meyer-Vietoris sequence.
That's right. Yeah, yeah. And that's what's failing here.
And you're sort of tacitly assuming that it means you have a cohomology theory?
Yeah, the other two axioms are satisfied automatically.
Yeah.
So the only thing to check is Meyer-Vietoris. Yeah.
And then I have a remark about this higher D. I mean, I think there's some feeling that for very large D, the only field theories are going to be related to cohomology theories, or some classical algebraic topology. In other words, low dimensions. The fact that classical algebraic topology couldn't solve the problems of low dimensions is why this quantum field theory is there to help us.
OK, but you can take like D equal to 4.
What?
You can take D equal to 4 in a lot of these examples. And it's not obvious a priori that those shouldn't lead to some.
I meant really high.
Oh,
10.
OK, well, you can't go much higher than 10 in these examples.
Right.
I think actually 10 might be the cutoff. I forget exactly. Need to check some spin 16 type representation theory. OK, there's also a story for equivariant theories. Which are also called gauge theories in this perspective. And that's pretty wide open as well, outside of the 0-1 example, where 0-1 EFTs that are equivariant are models for equivariant Theorem cohomology. So there's a huge amount of examples out here that just don't really seem to conform to standard techniques in algebraic topology. That's puzzling, but also it'd be exciting to figure out what's going on here. OK, so you might think, well, maybe it's just that these things aren't actually interesting, that they don't contain any interesting data, or that we can't pull it out of them. And I want to give you just one minor theorem that shows that there does exist something, some manifold invariant in these guys. And for that, I have to define what a sigma model is. And this, if you've heard the word sigma model before, that's great. If you haven't, this might seem out of the blue. I might try and explain it if I have time. But so the sigma model, or the d delta sigma model on manifold X is the image of 1 in d delta field theories over X under quantization. Okay, yeah, sure. So, great, yeah. Okay, so just to, this is over here. So if I start with y equal to a point in both cases, and I take just, this is some symmetric manifold category, I take its unit object and I quantize, that would be the 1, 1 sigma model of X. Similarly for these other examples.
So the sigma model is always something over a point?
Yeah, let's say, yeah. So, and let me give it a name. Okay, so then I can take what's called the partition function of this thing. So it's usually denoted z sub x or something like that. And you take this thing and you evaluate on a torus, sigma model. Okay, so the reason it's called a function is you can imagine varying the Euclidean structures on this torus and you get different numbers. Those should vary smoothly as you move around the moduli space of Euclidean structures on the torus. Everything's done to guarantee that. Okay, so why is this interesting? Kind of by construction. These quantization maps, the only way I know how to build them is by using the sigma model. And they're kind of built such that this definition conforms to what the physicists tell us a sigma model is. Arturo was discussing that the other day. If you take the trivial bundle and you quantize in dimension 1, 1, you see this Dirac operator acting on spinors. The trivial bundle is this 1 and 1, 1 Euclidean field theories, and the Dirac operator is the 1, 1-dimensional sigma model in some sense.
So vertical arrows are defined when y is a point, they're all d delta. Is this definition contingent on the?
It's contingent on the construction, yeah. So what is a quantization? I guess I should have given a slightly more precise definition. It should be, if I view this as a morphism of sheaves in the y variable, the quantization is a morphism of sheaves. And for every such morphism, I can define a sigma model.
So it is, or it like should be?
Oh, this is definition. And in these zero-dimensional examples, you can just brute force it. These, it seems very plausible that the analysis is manageable. These guys will require something new, these two-dimensional ones, except for maybe in this 2-2 case where you can get away with some kind of floor-type combinatorial construction. That's kind of the hope. So there's a definition, which is this morphism of sheaves. With this definition, this is the definition of sigma model. There are some examples of it. But they require the construction of some quantization.
So there's a variable, which is the quantization you choose.
Yeah.
There's a sigma model for every quantization.
Yeah.
I'm somewhat confused. I mean, for instance, in this middle arrow, I mean, usually you have to choose the manimetrical next.
Yeah, that's hidden in what a geometric spin structure means. Yeah, but that's definitely part of the data in defining this.
So then it can, of course,
When I pass to the homotopical data, that choice of Riemannian metric just goes away.
this definition, are all the parts mathematically defined?
Yes. There aren't that many examples of quantization, but when it's defined, this makes sense. Or when it's constructed, sorry, when it's constructed, this makes sense.
So if you translate somehow...
So that when it is defined under quantization, I don't want you to write anything, just,
yeah.
Is that what it means?
Yeah, exactly. So this...
You have a definition of quantization.
Yeah, so let me maybe put like a warning sign here. So this quantization, this requires a construction. Possibly difficult construction.
Wait a minute. When is the sigma model defined?
Sorry?
I mean, when it's defined, the sigma model has to be the quantization.
So first, okay, let me just say kind of the process here is I construct these quantization maps that are natural in this variable y.
But you don't know what elements you have in some of these cases, right? I mean, if you have a theory, you can have the map, right?
Well, you can ask for it, but I mean, this requires analysis. Arturo was discussing how this is some hard index theory type stuff, and over here it's even harder. So let's say that someone hands you some field theory together with this data of a quantization map. Well, then I can single out this element 1 when I set y equal to a point and look at its image under this map. And I'm calling that the sigma model. That's my definition.
Somehow don't agree with that terminology. I think to me, the sigma model is the stuff that allows you to write down this quantization model.
Yeah, let's discuss that later. I agree, but I don't want to belabor that.
Sigma model, then we call it the index.
Well, that's the partition functions, the index. There's a lot more data in the sigma model.
Well, it's kind
But they're different things. I mean, it's like equating a Dirac operator with its index. They're just not the same thing. Anyway, we'll discuss that later. I agree with your sentiment, and I think it's worth discussing, but I don't want to get into it right now. OK, so the theorem here.
Sorry.
Yeah, it's OK.
This map is what you're calling quantization?
Yeah. So this is right. So quantization.
Reducing the homotopy function, right?
It's a natural transformation between homotopy functors. This it's a natural transformation between these homotopy functors is what it induces.
Okay.
Right? Each one of these things is defining, if I take concordance, some homotopy functor from this definition of quantization, it respects concordance because it's natural in this y. And so it will induce some natural transformation of homotopy functors.
If you would define the spin x, redefine spin x y just as some hom from one sheaf to the other and sheaves over y's. I mean, then it would be just the evaluation map. Then it would be a true statement. Then, of course, you don't know whether this hom is non-empty or how to write it. Yeah, but then you could make, but then the question is the space constructible that you get always the same thing or something like this. But I mean, I think there is a way to make.
Yeah, sure.
Errors, not dashed errors.
Well, OK, I guess.
Interpreting what spin x, y is.
I mean, I agree that we can just ask for any morphism of sheaves, and that's the definition of quantization is any morphism of sheaves. I'm just saying that singling one out so you can actually compute the sigma model is hard.
Yeah, I think his point was like if you change the top thing,
yeah.
spin x, y to something else, then he claims you can make the dashed arrow a solid arrow. That was
Then, yeah.
OK, I want to hear more about that, but maybe after. Is that OK?
Of course, the question is whether the spin x is supposed to be much smaller than this hom.
It's the spin x.
I mean,
Confused what that means.
Specific idea what spin x, y is.
That's right.
Or is it still also?
No. This is totally defined upstairs. This is totally defined downstairs. These are specific sheaves on the side of manifolds. And I'm asking for.
Yeah, you can define another sheaf. Another thing, which is a hom sheaf from one to the other.
That's right.
Will it be equivalent? You don't have to know what quantization is, but it would be.
We need a section of that sheaf. I mean, that's the thing that's not so obvious, right?
Yeah, but
if I have a non-spin manifold, I'm going to have a hard time writing this down.
Both are empty, but.
Yeah.
Wait, my question is equivalent to question whether this error exists.
Yeah. Is that OK? OK. So, OK. So the theorem is that this partition function actually provides an invariant of the manifold X. So. And it's an invariant. You have to be a little careful. It's an invariant of the manifold together with a homotopy class in here. So for example, the A roof genus depends on the spin structure. Or sorry. No, OK. Yeah, there you go. Yeah, so a priori this might depend upon which orientation you choose in this quantization discussion. OK, so this shows that there are actually invariants for all d delta. We have to find out what they are. And it's not a priori clear. But this is kind of like just getting the index of certain operators. We'd actually like some kind of analog of the cohomology theories in which these things live. And I want to spend my remaining time describing that story.
Answer that sentence again.
Oh,
Dx
great.
Is an invariant of a manifold together with its orientation data?
Yeah, so isn't
I mean, is that what you mean?
yeah, an invariant of, yeah, sorry, is there, it's ambiguous, isn't it?
Manifold together with its orientation
Yeah,
data?
so if I have the pair, say, M and orientation, I can consider this up to homotopy of this orientation. And that's what this is an invariant of.
It's an invariant of that.
Yeah, yeah.
I don't understand in what sense it's a
Uh,
theorem. It seems like any functor out of the category of manifolds has the right to be called an invariant of a manifold. And like, so spin, you can think of this quantization graph as depending on like, oh, I see what you're saying.
why does
You're
this
saying it's
depend?
independent of the as if because you're taking a trivial bundle x cos y.
A priori, it might depend on data in here that's contractible.
So I think the theorem is equivalent to the assertion that this z of x is a concordance invariant.
Exactly, exactly.
You get downstairs.
Exactly. So that's all I'm saying is that this is a concordance invariant of the original theory. So,
of the thing downstairs. I mean, this is the thing you can prove. I mean,
well, yeah, but I'm asserting that it's an concordance invariance of the thing upstairs.
I mean, if you have something which is continuous, I mean, if this quantization existed,
Then it's continuous. So, OK, this is how the proof goes, roughly, just to say kind of what the ingredients are. You view this morphism of sheaves as a morphism of generalized spaces. You take pi 0, you look at the map on pi 0, and you show that it's well-defined, basically. So that is to say that if I vary the starting theory, I stay in the same number downstairs. And this number doesn't change as I go through concordances.
right, if quantization existed, then it's the theorem.
Well, this isn't even defined without quantization existing. So,
I mean, no, I mean, there's a functor. I mean, maybe you have one.
yeah, I mean, this depends on the choice of quantization. I totally agree with that. This number that you get. But seeing that it's a concordance invariance, I claim is actually not a trivial thing. No, I mean, it amounts to,
But there's an argument you do downstairs.
it's kind of like a Stokes theorem
I mean,
in a
this
sense.
is the thing you do downstairs. I mean,
Yeah,
somehow
but this is some giant
the thing is
space.
here that it is, you get, if you take equivalent things, then you get concordant things downstairs. So
Yes, but this is a number, and that number may not be a concordance invariant of the field theory.
Yeah, but there's something which has nothing to do with quantization.
What has something to do with the manifold? I'm a little confused by the question. Okay.
But you're not claiming that it's not true invariant.
That's true, but it is in examples. You have to compute it, yeah. OK, I'm going to have to blitz through the last little bit here. I'm halfway through the talk. OK, so what I want to explain is a way of recovering a cohomology theory from one of these sequences of field theories. So it's going to be sort of an approximating cohomology theory to this theory. So another theorem. So let's see. So there exists a functor or a contravariant homotopy functor. I'll denote T1 of d delta Euclidean field theories. This index k, satisfying let's see. So for any sequence of sheaves that does it have a Meyer-Viatora sequence and a map to d delta Euclidean field theories, Well, first I have that this thing lives over that guy, and that there exists a unique lift. So this is, let me just say, this is a sequence of sheaves over manifolds satisfying Meyer-Beer torus. Okay, so unfortunately I don't have a lot of time to explain the ingredients of this, but this should be viewed as some kind of Goodwillie derivative of these functors. This is a linear approximation. Okay, so I guess I should have said, oh, sorry, there exists a functor this, and this thing has Meyer-Beer torus sequences. Huh?
The map really go that way? The vertical map really go that way?
Yeah, it's funny, isn't it? It's a limit, not a colimit.
It's a co-Goodwillie.
Yeah. No, I agree. This is funny. I mean, it's basically that you want to preserve the sheaf property, which is a limit property. So you don't take colimits.
Oh.
Yeah. OK, so I guess I should have said a field theory is linear if it has Meyer-Beer torus sequences. And then, let's see, almost out of time. OK, I'm going to state a result that has a technical assumption that I'll not spell out too carefully, but basically says that the only linear, so subject to this technical assumption, the only linear field theories are the ones that were back behind this board. So these guys are the only examples. Yeah, so for d bigger than 1, or delta bigger than 1. If so this condition is roughly that quantization has some behavior with integration. So that's this condition. So what is this telling us? This is kind of a funny statement, I realize, but I don't have quite the time to. I mean, this is a precise condition that I can write down very carefully. But what this is saying is that unless some part of this picture is wrong, which is totally possible, then these homotopy functors for higher delta give rise to something more complicated than cohomology theories. Somehow they're objects related to unstable homotopy theory. So let me give just a final example as to why this might be. So I mean, this is an example I found after proving this, so this is one of these a posteriori things. But anyway, so one example why one might expect this is that for there's an inclusion of flat vector bundles with O delta actions, and parallel transport has to be equivariant with respect to that into 1 delta Euclidean field theories. So I guess these are flat vector bundles over X. So flat vector bundles, well, that's something about pi1. You don't really expect to see pi1 data in cohomology theories. So somehow the fact that these guys live inside of here means that, well, you shouldn't be expecting to see stable data alone. And so the real challenge, I think, in the coming years for this program is to understand how do you pull data out of these things and what homotopical information is contained in them. So I'll stop there.
Questions?
Yeah.
I know you didn't really want to say that much about quantization.
Yeah.
So I'll ask a question anyway about the quantization now. So you want it to be like the Tom isomorphism, or you want it to be sort of like the Tom isomorphism twisted?
Okay, so so I didn't even say what the extra data was in here that is this quantization. So let me just very briefly spell that out. It looks like
The diagram on the board. You want
Oh.
that, you want the square to commute, or you want the square to commute up to
this.
not that one on the hidden board.
Ah. Oh yeah. These squares shouldn't commute. These big ones.
Okay.
No. Because I mean, already we've got like Todd classes and A-roof classes turning up. That is the measure for that failing to commute. Yeah, so none of these diagrams commute. I guess, well, sorry, these little triangles do. These big ones may not. Turns out in some examples they do, which is actually really weird. I don't know why. These 0, 2 examples.
Not supposed to commute.
Yeah, they're not supposed to, but somehow with more supersymmetry, they sometimes do for reasons that are very mysterious.
Is that telling you something about sort of like the higher index theory in that sort of dimension? Is that it's more interesting?
Yeah, I don't know. In the 0, 2, and 1, 2 example, it's telling you that there's a local formula for the Euler characteristic, which maybe I should have mentioned that if you analyze this map kind of analogously de how Witten analyzes Morse theory and de Rham theory, he proved the Chern-Gaspinet theorem over here. And so you can see Witten's deformations of the Morse from the de Rham complex to the Morse complex is some kind of categorification of the Chern-Gaspinet theorem. So, I mean, here it's just kind of a miracle about Euler characteristic. I don't know why this commutes from a deeper perspective.
Other questions?